Hello everyone, and welcome to the webinar series hosted by Shimatsu, PFAS in Focus. I'm Ruth Marfil Vega, and I'll be with you during the 5 webinars that are part of this series. Per and polyfluoroalkyl substances, or PFAS, have been a hot topic for several years. With this webinar series, we want to distill the essential information on PFAS analysis, sharing our expert insights with you to help you navigate the challenges and succeed in your lab, no matter the current knowledge of PFAS that you have. I'm very excited to kick off this series today because at Shimatsu, we want to empower you with the critical analytical skills for you to become the PFAS expert in your lab. As I said, we are kicking off this 5 webinar series today, and I'm here with my colleague, Landon Beast, who will be presenting about how to master PFAS control in the laboratory. A few reminders about logistics before we start the presentation. The webinar console has a variety of items to help your experience and interaction with us during the presentation. In the screen, you are going to see the following items. The slides will appear on the middle. Right under the slides, you will find a resource list with clickable links that take you to materials relevant to the content presented today. On the top left, there is the widget for questions and answers. You can type your question at any time during the presentation, and we will answer them at the end of the talk. Below the Q&A box, there is a survey. You might fill it out anytime during or after the presentation. On the right-hand side are the moderator and speaker bios. You can expand the items to learn more about us. And finally, at the bottom pane are the icons to bring up all these widgets. In case you lose them, they are minimized or hidden. With that being said, I would like to reintroduce Landon Beast, the LCMS product manager here at Shimatsu Scientific Instruments, who will be our main speaker today. And now I'll hand it over to Landon.
Thank you, Ruth, and good morning to all of you. It's a pleasure to speak with you, and I'm hoping that you're here to learn a lot. The work in this presentation represents hundreds, if not thousands, of hours of work to try and simplify PFAS to make it easier for everyone, frankly. And so mastering PFAS control, transforming your laboratory practices, is going to be some first steps that will help you to be able to reduce the amount of PFAS and increase consistency and robustness of your method. So let's get started. Now, to talk about how to transform your laboratory practices, you first need to understand what things might need some transformation. So in PFAS, we know that contamination can hide anywhere, and those small places where it can hide can really affect the amount that you might detect in your standard or in the samples that you might bring in, and that can affect your results. So understanding where it's coming from and how to mitigate it is absolutely crucial. Sources before the autosampler include places like the solvents or buffers, maybe your tubing, or it could even be your degasser. These are common places where PFAS can exist, and there are very straightforward ways that we're able to mitigate the PFAS that come before the autosampler. After the autosampler requires also a lot of consideration. Places like vials, vial caps, or even other materials that they come in contact with your sample can affect the amount of PFAS that is detected. So we're going to describe to you today how to mitigate PFAS contamination in all of these places throughout your entire analysis. A good place to start this discussion especially for PFAS before your autosampler, is places like tubing. There's a lot of tubing throughout an HPLC, and because of its flexibility, PTFE is frequently used. It's pliable, it's robust, but it can leach PFAS, and that can be a problem. Therefore, PEEK and other materials are available to be able to mitigate this issue and eliminate this potential source of PFAS. I do encourage a bit of caution when trying to address things with a tubing kit. We've noticed that some people will try to bypass their degasser because degassers frequently have a lot of PTFE and can give a very high baseline of PFAS. What this can result in when bypassing the degasser is a kind of pressure trace like you see here on the right. This can result in air bubbles, and it can frankly mess up a lot of runs, and because you're not removing gas from your solvents, this can adversely affect your chromatography. This requires a lot of care in degassing your solvents, whether through sparging or through sonication. And so understanding what trade-offs you might be making is very crucial to just replacing the tubing with a tubing kit, and especially replacing the tubing that might even bypass your degasser. It does not help with mitigating other sources of PFAS contamination, however, because it's just the tubing and other places can still have PFAS, and so we need to find a solution that can help the entire system. What we've noticed is that the best solution to eliminate PFAS in the background that comes before the autosampler is to use a delay column. What this does is it separates the PFAS that are contaminants, and it is able to delay them so that your sample elutes first, and then the background contaminants elute later. In our example here on the right, PFBA comes out early, and then right after that, with enough resolution, you can see the PFAS from the background. This effectively eliminates the PFAS from your system, and when you have narrow MRM windows, it's not even seen. It doesn't affect the quantitation of your sample, and it makes it much easier to deal with potential PFAS contamination from anywhere before your autosampler. It gets retained or delayed in your delay column and then elutes outside of your MRM windows so that it doesn't affect any of your quantitation. The installation of this solution, this PFAS delay column, is very straightforward. All you need to do is install it in a place that will capture all of those potential contaminants, and we found that the best place to do this is after your solvent mixer, or the mixing chamber that brings both your A and your B solvents together and mixes them. By installing this column after that point, you effectively delay all of the potential PFAS contaminants from your solvents, your buffers, your tubing, and your degasser in an extremely effective way. We've engineered a solution at Shimadzu that actually adds very little back pressure to the overall system, maintaining the possibility of having a high performance or UHPLC column as your analytical column. This in no way replaces your analytical column, but it does enhance your analytical column's performance by delaying any contaminants, especially PFAS contaminants, that might affect your analysis. We even have a video of its installation online, and it can be easily found on YouTube. Now, we can tell you all day long that we have a really great solution, but let's back it up with some data, shall we? For this particular proof, we were able to do this with EPA 1633 as the method of choice. It's very rigorous, and we thought it represented our data very well and highlighted the efficacy of our solution. We did this on an LCMS 8060NX, which is a very sensitive LCMS, and we did it with a very typical configuration. We also wanted to do multiple replicate injections just to show the robustness of the system and how reliable it could be. What I would like to emphasize is that this was a standard configuration. We used a degasser, and that degasser and other tubing in the system contained a fluoropolymer, meaning that to be completely secure, we would need to have the delay column in place. We performed this experiment with no delay column to show a difference when we actually did use a delay column and we showed data with nulls and blanks and also a blank co-injection. Let's define some of those terms, shall we? A null, again, is where you run your entire chromatographic method, but you don't move any valves. So you're getting a full system diagnostic and get to see the baseline without any moving parts. A blank is when the autosampler actually injects some kind of solvent that intentionally doesn't have any sample in it, so that you can just see how clean your system is when the autosampler is being used. And then a blank co-injection is a way to be able to do a blank, but you also put in some air gaps or other solvent to be able to improve the efficacy of your injection, which can help with sample introduction onto your column. The calibration curves here were compound dependent, and we had different ranges as seen here, whether we did a standard injection or a co-injection for PFBA. Now, here's the data. Without a delay column, which is shown here on the left, it's very apparent to see that all the system contaminants of PFBA are eluting with the sample. Once we put the delay column in place, you can see that there is a little bit of PFBA with maybe some of the blanks, indicating that the solvent might have some PFBA contamination. Now the delay null, which is best seen in blue, it's clean. So you know your system is clean of any PFBA contamination, but that your blanks might have some. And of course, if your blanks have it, the co-injection will as well, and they overlap very well. Once we inject the standard, we now know that we have a better ability to quantitate PFBA because it is separated from the PFBA contamination. It's fully resolved, and we know where the PFBA contaminants are coming from. We wanted to show you some very real data because there have been times when some of our solvents are contaminated and we mitigate that, and there have been times when they're not, and then we can move forward. In this case, I would advise that you find better solvents that don't contain PFBA so that you can get more quantitative results, as this indicates a tiny amount of PFBA contamination. Now, of course, if it's below your MDL or MRL, then you're going to be okay. But this is a way to help diagnose your system and some real data that we experienced and wanted to share with you. At this point, I propose that we take a full-on dive into delay columns. It's a metaphor, of course. We have analyzed several to help you understand which ones we think are the best and most effective. Now, because it's 2024 and we went through the Summer Olympics, we wanted to make this an Olympic-themed presentation, and so we are going to show which columns got first, second, and third place and award them the appropriate medals. While we collected all of this using a 1633 method, what we did was choose analytes that had a lot of similarity with other EPA methods like 533 and 537.1. We tried to choose as many chemicals that had a lot of overlap as possible. Now, some of them are specific, but that's because they are also very difficult to remove from a system because of how common they are in our environment. As you can see, we detected these PFAS in our background: PFBA, PFHXA, PFPES, 6,2-FTS, 7,3-FTCA, 9-CL, PF3-ONS, all of them were detected. And looking at our scales here, they definitely could affect our quantitation. Without a PFAS delay column, these would have adversely affected our chromatography and would have given false results. Once we installed the delay column, we were able to delay these contaminants and remove them completely from our quantitation window or from our MRM window entirely. You might see a couple peaks with the PFPES or the 6,2-FTS, but those are just signal noise. Looking at the scale, you can see it's 20 counts or that level. So there's no need to worry. This is just a detector showing some noise like they always do. But the point of this is that the delay columns work. And so we're going to get more specific with which delay columns seem to work the best. Now, I know I keep on setting up this case, and you might say, when are they going to show us the actual columns? I'm almost there. but I want to describe to you first what matters in a delay column. You can't just use any column. What are the attributes we are looking for specifically? First of all, it needs to have enough volume to be able to retain any contaminants that might affect the peak when you integrate it. And so you would prefer to get it away from your actual peak of quantitation, and it's best if you can completely get it out of your MRM window. What this requires is a stationary phase that has enough retention of the PFAS and silica that actually has enough surface area. There also needs to be enough internal volume in the column to be able to affect this delay, but that's also a balancing act. You don't want too little and you don't want too much. It's also important that the column have high pressure capability. A lot of columns that are made that have low pressure drops are also made with column housing that can only experience 4,000 or 5,000 psi, resulting in your delay column failing. So you got to fix that. It's also important that you have a silica that is very mechanically stable so that it doesn't crush if you're using UHPLC pressures. Also, you want minimal pressure contribution. This is so that your analytical column can contribute all the pressure it needs to, and your delay column is performing its function the best it can. The things that contribute to pressure are your particle size, your column diameter, and your column length. So the bigger your column diameter, the shorter your column length, and the bigger your particle, the better you're able to actually decrease your pressure. So different delay columns can work, but there are some that work better. If I were to look at this particular peak here, I would say both of them pass. I like both of them, but it's clear that one of them is a bit better. Both result and give passing data. There's no question about that. But if you were to choose the one on the left or the one on the right, which one would you pick? I'd pick the one on the right because it just gives baseline peak shape and it doesn't affect the overall chromatography nearly as much as the one on the left does. Even though they're both doing a good job, I think the one on the right does a great job. We also realize that labs are often doing multiple methods, and to keep track of which delay column works where can be a real pain in the neck. So, considering that each of these methods is drastically different, we want to help you understand which delay columns work best for each method. And so we want to try to minimize that as much as possible, and you'll be able to know our full results as we show you the actual columns and their performance. So stay tuned. We're going to get to revealing which of them work best for each of these particular methods. Also keeping in mind that you want to have as few delay columns as possible. But each of these methods is different. Each of them have different requirements, and some are for water and others are for other sources like soil. So it's not immediately straightforward, and you need to just choose very carefully the best materials for your separation. Giving a little more detail, our EPA 1633 tests, which were done in-house, and as said previously on the LCMS 8060NX, had 5 different delay columns tested. We did this again with standard tubing and standards from our EPA Cal 1 or our low calibration point. Our injection volume was 2 microliters, and we did this with 9 different replicates. I mean 7 replicates, pardon me. When we did our EPA 533 and 537.1 evaluations, we sent selected delay columns to greater than 4 customers, and their configurations varied. Some were on an 8050, others were on an LCMS 8060, or even an LCMS 8060NX. Their configurations also varied. Some used the PFAS tubing kits, others bypassed the degassers, some used the degassers, some just used standard tubing. But the point is, there was a lot of flexibility that was demonstrated by these columns, increasing their utility actually. And we also did standards and samples. We didn't just want to give these an easy time with standards, and so samples were actually employed because those contain more stuff. And so, as mentioned, we have evaluated these with the EPA methods and really put these columns under real-world conditions. Bringing all of this together, we evaluated various parameters to help us determine what we viewed to be the best delay columns that we tested through these battery of tests. The 4 parameters were the max pressure capabilities, the back pressure contribution, the peak asymmetry of an early eluting peak, and the overall lifetime or resilience of the delay column. And now presenting our competitors. For today's PFAS delay column relay, we have in lane number 1 the GIST 5 micron 50 by 3 millimeter delay column. Lane number 2, the NextCall 5 micron 50 by 3 millimeter column. In lanes 3, 4, and 5, we have the Scepter 3 micron family, the 50 by 3, its skinnier brother, the 50 by 2.1, and their longest relative, the 100 by 2.1. It is surely to be an exciting competition today, folks. Let's see who comes out on top. Okay, let's get back to business. Thank you for that fun moment of getting to be a sportscaster. Let's talk about pressure traces. For this particular analysis, we used a Scepter analytical column that had a C18 bonded phase with 120 angstrom pores. The particle size was 3 microns with a column of 2.1 millimeter inner diameter and a 50 millimeter length. We tested the 5 different competitors and showed these following pressure traces. Looking at the pressure trace that is the highest, it makes sense that this would come from the Scepter 3 micron 100 by 2.1 column, because this has all the attributes that are going to increase pressure in comparison to the other competitors. The Scepter 3 micron column has a smaller particle, a longer length, and a narrower inner diameter that's going to increase pressure. Comparing this to the NextCall and GIST columns, which are both 5 micron particles, or contain 5 micron particles, and are housed in a 50 millimeter by 3 millimeter inner diameter housing or column, we can see that there's a drastic difference. On the top, we're hitting 4,000 psi with the Scepter 100 by 2.1. This means that lower end or older HPLCs might not be able to run this because sometimes the pressure threshold for those is 4,000 psi. On the other side, we have pressure drops of lower than 2,000 psi, showing that the NextCall and GIST columns win this pressure trace argument for this analytical column. And if we really need to look at this photo finish, the GIST column ends up winning here for pressure drop. This next test is using another Scepter analytical column, but this time we are using a sub 2 micron particle. Pardon me. With the same competitors, we see a similar trend, but if we are to use a UHPLC column, this increases our pressures to above 5,000 psi. If we were to lengthen our analytical column, it would just increase the back pressure. This helps us to understand that we really do want a delay column that contributes as little pressure as possible, and that can only happen with the NextCall 5 micron 50 by 3 or the GIST 5 micron 50 by 3. Again, in this very close race, the GIST comes out just slightly ahead. Pressure is only one factor that we're looking at here, and we need to also look at how they actually perform their function in terms of being a true delay column. For this, we wanted to see the influence of these delay columns on a solvent blank, and we're looking at PFBA in this instance. The shim pack on the left had insufficient delay. We can see a very clear contaminant peak come out right where we would expect the analyte to elute. Now the shim pack in the middle has sufficient delay, but it's got a very high baseline, which is undesirable. The NextCall column has good delay, and also a lower baseline, which makes the next call win in this particular instance. It's a fair question to ask what makes the difference here. And that is because the 50 by 3 column has a larger volume. When looking at delay columns, you're not so much wanting to look at plates per meter, but you are wanting to look at the volume of the column. That will also mean the amount of delay power that you get because of how long those contaminants will reside in that column. The phase is also important because it will interact and slow the PFAS down, but that is a crucial thing to have an effective delay column. So here we want to have low pressure and sufficient delay, meaning that a larger column is better, but having a larger column also means that the changes that happen at your pump, like a gradient, will take longer to get to your analytical column because you're increasing your dead volume. So again, this requires some amount of balance, and we found that the 50 by 3 gives us the best of both worlds. In this case, the next call, 5 micron 50 by 3, is the clear winner. To determine the resilience of these columns, we were looking at the number of times that they failed. Usually they fail by getting high pressure, which originates at the delay column. If you're familiar with guard columns, you put those in front of your analytical column because they catch the matrix and other contaminants that could affect your analytical column. Some contaminants can also come from earlier in the system, and so the delay column is going to catch those first. This results in high pressure that originates at the delay column, and then the delay column can either cause a pressure failure or a leak, or it can even have adverse effects on your chromatography. The failures can be caused by mobile phase contaminants or other things that might be coming. If your pump seals are deteriorating, there's a lot of different things that can factor in here. And what we've noticed is that smaller particles foul more quickly and narrower columns increase in pressure more rapidly. And so these high pressures cause column stress, also meaning that you want to have a housing that can withstand high pressure so that when things start to deteriorate, you have a longer time to be able to still function before a full system failure occurs. So looking at the resilience, we can show you the results that came from testimonials both in-house and from the field. Now, this is a little bit of an extrapolation of column failures per year. We did this over a course of several months, but to make these numbers make a bit more sense, we're doing this on a per year basis. Now, I will make the acknowledgement that this is quality of solvent dependent, and it's also dependent on your good lab practices. And so this was just average data that we collected from all the columns that we used and tested inside our lab and with some of our partners. We noticed that the scepter columns, when used as delay columns, failed more frequently, kind of on a monthly basis. And so we didn't see those as great candidates for delay columns. When used as analytical columns, they're actually very good, but as a delay column where they're experiencing different stresses, they didn't perform as well. The clear winners here, again, were the columns with bigger particles and with a bigger inner diameter. The GIST and the next call both performed very well, but the next call, 5 micron 50 by 3, edges out the competition and seemed to have an average lifetime of about 3 months before it needed to be replaced. So to summarize all of the results here, it looks pretty clear. We have 2 columns that are competing very well as delay columns. Now, we would not necessarily choose them as analytical columns because they wouldn't have the best efficiency, and they might require a higher flow rate to work the best. But as delay columns, where they are performing a different function, the GIST and the next call performed admirably. The scepters actually work very well as analytical columns, but they have different requirements. Just as we have seen with some of our favorite swimmers, like Michael Phelps and Katie Ledecky, some strokes and some distances they're competitive in, but they're not champions, and other places they just blow out the competition. In this particular instance, it's clear that the 50 by 3 millimeter columns with 5 micron particle sizes are the champions for our delay column competition. But when awarding medals, the medals go to the Shimpact Scepter 3 micron 50 millimeter by 2 millimeter inner diameter column for the bronze medal. The silver medal goes to the Shimpact Gist 5 micron 50 millimeter by 3 millimeter, and the gold medal goes to the Next Call 5 micron 50 millimeter by 3 millimeter inner diameter column. Congratulations to all of our contestants. You all did wonderful. After the Next Call has won this gold medal in a very tough competition, we wanted to give it some victory laps and show its performance with the 3 EPA methods, 537.1, EPA 533, and EPA 1633. What we're showing here is the lowest calibration level, and we're showing very clean chromatography in all cases. Great job, Next Call. This slide here shows additional PFAS at the lowest calibration level. Common things like HFPODA or Gen X, PFOA, PFOS, PFHXA, PFBA, and 62FTS. All of these pieces of data were pulled from their respective methods and show very good peak shape for the system that we have here. I would even highlight the PFOS, which has isomers, and there is some very good resolution between the linear versus the branched isomers. This indicates that the Next Call delay column actually works very well for all 3 EPA methods. Now let's return to this slide that we've seen in the past. What has the delay column helped to mitigate? It's done its job. It has delayed the PFAS contaminants that have come from solvents, buffers, tubing, or even the degasser. It's important to note that these all occur before the autosampler. PFAS contaminants that are introduced after your autosampler are impossible to remove because your analytical column is going to see them, and then it's going to be detected by your mass spec. In this case, it's important to test your consumables. The ones that come after the autosampler that are some of the most likely culprits to contain PFAS are your vials, your vial caps, or any materials that come in contact with your samples. These can be things like your pipette tips or your collection containers, and also things that might happen through shipping and preparation. Care is required every step along the way to prevent contamination of your PFAS samples. And now we have been able to show a way to mitigate many of these prior to the autosampler, but after your sample's been introduced, it's important to evaluate all consumables. We're coming to the end of our time together, but I wanted to give a few shots before closing out this presentation. While we have talked about PFAS contamination, it is also important to talk about solvent grade. PFAS contaminants in your solvents are one thing, but solvent grade is an entirely different thing. Here we show several different analytes and the percent RSDs that we observed, and the only variable we changed was, frankly, our solvent grade. When using LC grade, our percent RSDs, when looking at peak area, were routinely larger for some of these compounds when using LC grade acetonitrile versus LC-MS grade acetonitrile. pretty much across the board, we got better data when using LCMS grade acetonitrile than LC grade acetonitrile. This made our runs more robust and reproducible, and we also had to do less maintenance on our system because the solvent was just more clean. A lot of people will make the choice to go with LC grade solvents because they're cheaper versus LCMS grade solvents, but you very quickly lose that savings in the cost of instrument downtime and sample throughput. So this is something we would strongly urge you to consider, and would advise you that you should purchase LCMS grade solvents to improve your data quality and reduce your instrument downtime. One more thing to consider. When looking at the FTS compounds, we noticed that they were very sensitive to mobile phase lot variability. Even when we were using LCMS grade solvents, if we had to do a solvent change in between runs, in between calibrations, we would sometimes observe a drastic difference in our CCVs. As seen here, the pink shows the area of a CCV after the change of the mobile phase, but before we changed it, the area was much lower, and it can go the other way too. Different lots of solvent can affect the signal intensity that you observe. And while it seemed the FTS compounds were the most sensitive to this, we did observe it in some cases with other compounds. The way to fix this is to ensure that you have enough mobile phase to complete your battery of runs over multiple CCVs. And so making larger amounts of solvent is advisable in this case. But don't make so much that you're likely to incur some kind of microbial growth. Again, it's just important to know what your throughput is and make the appropriate amount of solvent for that level of throughput. My final thoughts today are, remember that a delay column is actually an analytical column. It's placed before the autosampler and after the solvent mixer, but it has the same kind of technology. Accordingly, delay columns do fail, but a way to extend the lifetime of your delay column, and frankly also your analytical column, would be to use a guard column ahead of it. It's due to those contaminants that gather at the head of the column that they usually fail, and so if you put a guard column in front, you can protect your investment a bit more. It's also important to understand that delay columns aren't interchangeable, and you only really want to try to swap them out if their inner volume is about the same. In our experience, 100 by 2:1 columns have about the same inner volume as a 50 by 3. You can do the math, and it comes out very close. This means that if you change out your delay column, you're likely going to need to evaluate your gradient because of the delay from the pump to your column, or that dead volume that exists. And so that delay volume is crucial to factor into the kind of delay column that you have and make the appropriate adjustments. It's also important to understand that troubleshooting the performance of a delay column is a bit more difficult than an analytical column. You can see the changes in peak shape, but as you saw today, those changes were very subtle. And so understand that we've given as much advice as we can on the performance of different delay columns, but understanding how that manifests itself in your detection after the analytical column can be a bit of a challenge. So we've tried to do some of that lifting for you today. And with that, I would like to thank you for staying with us this long. There are some people that we need to acknowledge. My colleagues, Kathleen, and Megan were instrumental in pulling off and gathering all of this data so that we could present it for you today. And without Dr. Marfil Vega championing us, we probably wouldn't have been able to get as far as we've gotten. So we thank her, and I thank my team for the tremendous efforts they put in so that we could present this for you. And also, I would be remiss if I didn't thank the customers and teams in the field that also were testing out these columns and giving us data so that we could get as broad a study as possible and give you some excellent results. And finally, thank you. You've chosen to spend some time with us here today, and we really do appreciate that. If you have any questions, feel free to reach out to me or to Ruth, and we'd be happy to answer them to you if you have any things that you need to ask us after our Q&A today. And so with that, I hand it back to you, Ruth.
Thank you, Landon, for your wonderful presentation and for opening the Shimatsu series, PFAS in Focus, with what we want to make all of our listeners the PFAS experts in their labs. If you would like to see the topics that we'll be covering in upcoming webinars, scan the QR code in the screen to get that information with the specific days, speakers, and register for the webinars. During the next presentation on December 19th, we'll be covering EPA methods 537.1 and 533. They are the key methods to support the PFAS National Primary Drinking Water Regulation. And now I would like to open it up for Q&A with the questions from the chat. As a reminder, if we don't get to answer the questions live, we will follow up by email. Let's start with a generic question. I got a couple of questions from the Q&A box mentioning specific delay columns, but Landon, the question for you is, if I have a delay column that I'm using now, what do I need to do with my method if I want to change the delay column and start using the next called one that was the winner in your presentation?
That's a great question, Ruth. So what you'd need to do is consider, is it a bigger or smaller volume? The next call is a 50 by 3. And so if you're transferring from a 50 by 2.1, what you'll need to observe is, well, first of all, you probably widen your MRM windows and run the same gradient and see what happens. In this case, your compounds will probably come out later because the delay volume is greater in a bigger delay column. Conversely, if it's going from like a 100 by 3 down to a 50 by 3, things will maybe a little bit earlier. And so in that event, sometimes all you have to do is change your MRM windows by just widening them and then centering them around the new elution time. So that would be the first step. If there is other complication that occurs, you might need to change the slope or speed or even the onset of your gradient. But those are just a few tips and tricks. And if those things aren't really working for you, give us a call. We're absolutely happy to help and give any pointers to any of those kinds of issues that you might face.
Thank you, Landon. Another question about the delay column. Is there any failure sign or any parameter that analysts should look for to identify that the delay column is having problems? You said in your presentation that the delay column and the analytical is another column like the analytical, and we normally pay more attention to the analytical column, but the question is very important. What are the signs to identify that the delay column is the one that is failing?
Mm-hmm. The first and best indicator would be pressure. If you seem to have really high system pressure, it's great to pull off your analytical column and see what your pressure is then. If it's too high, because ideally you should have a baseline for what your pressure is before your analytical column goes on, then you can start narrowing down where things might be. If you pull off your delay column after this point and the pressure problem goes away, then you might have a clogged delay column and it's time to replace it. So that's kind of how I would look at things first, but always just tracing things logically with the pressure. is quite crucial. The next thing that I would look at is if it's getting older, if it's bleeding, PFAS, if something like it's getting old, columns do age, you'll see a higher baseline potentially. And again, if changing out your analytical column doesn't fix it, then maybe switching out your delay column will. And there's a surefire thing. If you're seeing leaks, then the delay column also has probably failed, but that is something that we've tried to address with the hardware in this next call solution.
Good. I wanna remind the audience that you can still submit questions in the Q&A box, or if you have any follow-up comments from the answers, we'll be able to see them. Another question about delay columns before moving to consumables and other topics. Ladon, you mentioned during the presentation delay column, guard column, analytical column, and there were a couple of comments in the Q&A box about the placement of the delay column, and I'm going to go back to the slide that shows the picture. While I find that slide, can you confirm where Absolutely. Is the placement of the three things: delay column, Sure. Guard column, analytical column?
Sure. So let's start early in the flow path. The delay column is installed after your solvent mixer, as shown here. Then after your delay column, the flow will enter into the autosampler. And after a sample introduction, and likely back into your column oven, you will have your guard column set up and your analytical column. And those should be coupled or linked very closely together. I know some systems have an inline guard. Other systems have a guard column that attaches to the head of an analytical column. But that's typically the order that you would have it in. I might consider putting also a guard column on the front of your delay column. I don't want to confuse things too much, but just it's a way to protect your investments, because the guard columns will be cheaper than replacing a delay column or an analytical column. So I hope that clarifies things.
And I don't think we can see it well in the picture on the screen, but just to make sure that the audience understands, both the delay column and the analytical column are placed inside the oven. And that helps with the reproducibility of your results, especially in your laboratory, the temperature changes at night or in between summer and winter. Mm-hmm. With this setup, you make sure that you are going to have constant conditions for both the delay and the analytical column.
Yes, I'm very glad you brought that up. It helps the delay column to also serve a little bit as a solvent preheater and just gives much more consistent results keeping it in the oven. I've seen some setups where they do put it in the ambient air, and in that case, things can be inconsistent, as you said, if there are large temperature changes that occur in the lab. And sometimes air conditioners or heaters turn on and off, and so that can certainly affect your retention times because of the effect temperature has on a analytical separation. So that's a great point, Ruth. Thank you.
Okay, let's move now to consumables and solvents. You mentioned those during the presentation in their relationship with PFAS being present in the background. Mm-hmm. What are your thoughts? Are there? I don't like to see PFAS-free consumables because we know there are thousands of PFAS. But as we like to say, are there consumables where PFAS have been tested, and we can say that the selected PFAS are below a detection limit?
Right. So I am aware that on the market there are a couple places that have certified PFAS-free consumables, and my assumption would be that if they're proven not to be PFAS-free, there's a guarantee you could take advantage of. We're aware that PFAS is everywhere, and it could just be that for the systems they tested it on, that you just can't see the PFAS that might be there. For the consumables that we offer, we have tested them and several different lots of them and have found that we do not see PFAS on our system that comes from these consumables. We don't say they're PFAS-free, but they are recommended because they are low PFAS, or we have not seen PFAS on them. So there are sample vials, sample caps, and solvents that we have looked at. Pipette tips can be a source of a lot of PFAS contaminants. It can be anywhere. So I would be careful of any place that says it's PFAS-free unless they're certifying it and have a guarantee. But we certainly do have recommendations that we can share with you, part numbers for sources that have routinely been free of PFAS or low enough levels that we can't detect them on our sensitive instruments.
Yes, as Landon said, we've done extensive testing and partnered with different vendors to make sure that we have consumables that are suitable for the different methods, starting from vials, caps, the pipette tips, the buffers, everything. Feel free to reach out if you need specific details on how to get those. I'm going through I started moving the window with the questions. Let me see. We have the consumables. You have, Landon, another question. Do you have any suggestion of best practices to help with contamination after the autosampler? And I'm assuming that means that, after the autosampler, the only source of PFAS is the sample itself. And I'm assuming the question might mean that if you have, for example, really high concentration of PFAS and you saturate your instrument, your mass spec.
Sure. So in terms of places after the autosampler where you can deal with contamination that happens after that, I have noticed it can get stuck in valves. So yeah, this is a good place. Within the autosampler, you go, obviously, a needle where some apparatus goes in, aspirates a sample, and then injects it into the flow path. To do this, there are valves. And so if the valves are getting old, those can generate dead volume. PFAS can reside there. So making sure that your valves are clean or new can certainly be helpful. And so the high-pressure rotor valve in particular that is on most modern LCs is a certain place you would want to look. I've also noticed that the tube that comes from that valve to your analytical column, sometimes buffers or things, if people don't flush their system, it can get a little bit clogged. So that tubing certainly can be a place that you want to check for contamination. And then again, analytical columns can also age out. And so those are the only places I foresee that there will be some PFAS contamination, not just coming from your sample, but that might be existing in your system. So it's a good question, but it's very manageable.
How would you manage it? What's the recommendation?
Sure. Replace your rotor valve, replace the tubing, or replace your analytical column. And then if that doesn't seem to do it, then you might want to do a blanks test with the actual consumables, because maybe your caps, your vials, your solvents may be contributing to the contamination. I guess the only other thing I could think of at this point would be the line after your analytical column going to your mass spec, that somehow maybe it is contaminated. But usually I find working your way backwards and eliminating variables, basically starting at your mass spec inlet, going to your column, going to the tube from your sampler to your column, and then going to elements inside your autosampler, like your high-pressure check valve, it's best to start at the end and work forward. So that would be my way to interrogate that.
Thank you. Also, I think before changing different parts, flashing the system, and you can contact us for a recommended method to flash the system could be useful to try to eliminate or to clean out of the system some of the contaminants that can accumulate.
Yeah, that's also very good guidance. Thank you.
Okay, I think we have a couple of more minutes for another question. Okay, we talk about delay columns, we talk about consumables, not only testing the consumables to see if there are PFAS in the background, but as Landon was mentioning at the end of the presentation, making sure that the quality of the consumables is good, so the response of the analytes is optimal. Kind of related to general performance of the methods. Do you have any recommendations for PFAS analysis in soil samples?
So PFAS analysis in soil samples, that sounds like a 1633 question to me. And there might be some other methods out there too, but that's the one I'm most familiar with. Just be careful. It's not an easy method. So it's, well, what kind of recommendations are they looking for? I mean, there's so many ways to approach this, Ruth. Are there any other details given?
No, actually, I don't see anything. Let me scroll back to the question. No more details. So.
Okay. Well, I would love to answer that question for whoever asked it, but I think that figuring out exactly what the recommendations would be, if it's how to set up your MRMs or to get better signal from your analytes, if it's about contaminants, all of those are a different way to approach it. And we have experts here that can answer any of those questions. It's just great to know which of the recommendations are being looked for, because there are so many. I know that in soils also there are extraction methods. So we've partnered at NEMC. We had a talk where we had partnered with CEM for soil extraction. So again, it's like, what part are we talking about here? Because extraction is part of it, analysis is part of it, method development can be part of it. And we do have a method we recommend that we employ here. So just any of those particular details, we can dive into it later. And I think we might even have a 1633 presentation coming up, don't we, Ruth, in the webinar series?
Yes, we do. And I'm going to load the slide again just for a reminder to everyone. This is in the screen. You can see again the schedule of the upcoming webinars. December 19th, drinking water methods. January, in the new year, we are going to have 2 webinars talking partially on the soils method 1633 on January 9th and January 23rd. A little bit of different sample types with different ASTM methods. So I invite all of you to register for the upcoming sessions if you haven't done it so, and learn some more tips and tricks to improve the performance for soils and all the other matrices, including consumer products, later in February. I think we are 1 minute before the end of the webinar. Let me check once more. if there is any other question. Unfortunately, we don't have time to answer more questions live, but we'll get back to everyone that we couldn't answer by email. And at this point, I would like to thank Landon again for his excellent overview of how to manage PFAS in the laboratory, especially within the LC-MS. And thank you to all of you also for joining us in this webinar, the first one of our PFAS in Focus series. You'll get an email with access to the recorded version of today's event, and see you on December 19th. Thank you, everyone.
Thank you. Bye.